Good everyone, you're welcome back to the channel. Today we're going to look at this topic, divergence of a vector, right? Very briefly, we're going to look at the topic divergence of a vector. Now, the divergence of a vector at a given point, any point, measures the difference between the amount of flow out of that point and into that point. Okay, measures the difference between the flow of the vector quantity itself out of that point and into that point. All right, so I'm going to just modify this definition since. All right, so let's just say the divergence of a vector at a point measures the amount of flow out of that point. All right, now if there is more flow out of the point than there is flow into that point, then we can say that point has a positive divergence. That is, the vector is diverging away from that point, flowing out of that point, right? But if there is more flow into that point than there is out of that point, then we can say it has a negative divergence, right? That is, it's converging, the vector is converging towards that point or contracting at that point, right? Let's take an example of this. Let's look at this vector field now. I have 2 points, right? And let's assume this first point here, the vector, okay, we can assume this is an electric field, right? Electric field or magnetic field, whatever vector field you want to take into consideration. But let's just look at this field now, this vector field, and I have 2 points, these 2 points, right? And if this point, this given point now, I have outward flow, all right? Outward flow, that is flow away from this point, diverging away from this point. All right, I can say this point has positive divergence. Positive divergence. All right, and we call those points with positive divergence the source. All right, so I can call this point the source. Okay, since we have flow out of that point, and then we're also going to have other points whereby there is inward flow. All right, there's flow going into that point. And that point is said to have negative divergence, right? And they're called sink. All right. Then there are some other points too in a given vector field whereby there is no flow into or out of. You just have flow passing by that point. Okay, let's say I connect this to this point, this to this point as is usually represented in all these vector fields, right? And we have flow from this point to this point. Flow, all right? There's flow from the source to the sink. Now let's consider this random point. You can see that there is no flow into that point or out of that point. There's just flow across that point. Now the divergence at this point is 0, right? There is no divergence at this point. The divergence at this point, the source, is greater than 0, right? That is going to be positive. The divergence at this point, the sink, is less than 0, so it's going to be negative. You understand? But the divergence at points like this, points that don't have inward flow or outward flow, is going to be 0. All right, so source and sink, to just help us understand better, look at this tap, right? The kind we have in our bathrooms or kitchen or wherever you have them. Now this is going to be our source, right? Because we have outward flow of water, right? We have outward flow, and then we have inward flow, right? Outward flow, that's the source, right? Source, inward flow, that's the sink. Source, sink. All right, so that will be all for the theory, right? The divergence of a vector measures or tells you if there is outward flow or inward flow at that point, right? You can find divergence of a vector at a given point. All right, so and it's given by this formula. The divergence of vector v is the partial differential, or let's say sum of partial differentials of each component of that vector. You understand? The partial differential of each component of that vector. Now we're going to take an example to explain or understand this formula. All right, so let's see how we're going to apply this formula to solve this question, right? Find the divergence of the vector v. This is what the vector is giving us for, okay? Xy square I, that's for the I component, 2xz, that's for the j component, right? Then 4 minus z square y, that's for the k component. Now this vector can actually be written, you may see it appear in this form, right? Instead of this format, they may express it as this format. Now this is the I component, this is the j component, okay, and this is going to be the k component. 4 minus z square y. Okay, then you may see the question coming out with this format or this format. It just means the same thing, all right? Find the divergence of the vector v at the point 1, 1, 2. Okay, that's x is going to be 1, y is going to be 1, and z is going to be 1 at this point. Now, after solving this question, we would be able to tell if this point is a source or a sink, right? Depending on the nature of the divergence we're going to get. Is it a positive value? Is it going to be a positive value or a negative value? All right, so let's solve this. Now, the divergence, okay, the divergence of this vector is this differential, right? The sum of the partial differentials. So the first partial differential is going to be the differential with respect to x, right? And then the next one is going to be the differential with respect to y, right? And then finally the differential with respect to z, okay? Then we have this scalar product here. Then what's the vector v? That's x y square. As for the I component, then we have 2xz, that's the j component, right? Finally, we have 4 minus z square y, and that's the k component. All right, so let's carry out the scalar multiplication of these two terms here. All right, so this is going to be multiplying this is going to be multiplying this, and this is going to be multiplying this, right? So firstly, we're going to have the partial differential of x y square with respect to x, right? That's what we're going to have first. Then we're going to have the partial differential of okay, the partial differential of this 2xz with respect to y, and then finally we're going to have the partial differential of 4 with respect to z. All right, now that's how you apply the formula. That's it. From here, I believe you know what to do. From the previous video, we talked about partial differentials. You know how to differentiate this, right? So let's differentiate this with respect to x. Now y is going to be a constant, you remember, right? Y is going to be, okay, y square is going to be a constant. So the power of x here happens to be 1. You multiply that with the coefficient of x, it gives you y square, right? Then you reduce the power of x by 1, x is gone. All right, now let's differentiate this with respect to y. Now currently, okay, as you can see, there is no y there, so the power of y is actually 0. So 0 is going to multiply and everything is just going to result in 0. All right, the differential of this with respect to y is going to be 0. All right, now let's differentiate this with respect to z. With respect to z, now we have like two terms here. We have 4, which is just a number, right? A number, a constant. You differentiate this with respect to z is going to be 0. You differentiate this now, this term here, negative z square y. Differentiate that with respect to z. What are you going to get? Now you're going to get, okay, there is negative there, right? I'm going to multiply the power of z with the coefficient of z, that's negative y. So I'm going to get negative 2y. It was negative y. I multiplied the coefficient of z with the power of z, right? It became negative 2. You understand? All right, so this is going to be z. We reduce the power of z by 1 as usual. All right, it becomes 1. So this is what we get. All right, finally, this is what we're going to get. Y squared, okay, minus 2yz, right? Okay, normally this is the deviation of the vector. This is actually v, right? The vector we're given is v. The divergence rather of the vector v is this, all right? But at the point, we are given a point. At this point, 1, 1, 2. it is going to be 1 square. So this xy, x is going to be 1, y is also going to be 1. There is no x here, so we're just going to substitute y and z, right? Y is going to be 1, y is still 1, then z is going to be 2, right? So this is 1 squared, that's 1, minus this is 2 times 1, that's 2, times 2 again, that's 4. So finally we're going to have negative 3. All right, so what does that tell you about this point? We're getting a negative divergence here. The divergence of v at this point is negative. So what does that tell you? This point is actually a sink, right? A sink, as there is flow into this point rather than out of this point. All right, so we're going to take another example, and that will be it for divergence. So we can look at color vector in the next video. All right, so let's get another example and solve. All right, so this is going to be our example 2, right? Find the divergence of the vector. That's the vector, right? I hope you're not confused. They expressed it in this form we talked about. You can decide to convert it from this format to the IJK format to just avoid confusion, if any, right? But then there is no specified point. What's going on here? There's no specified point. Now the vector they are talking about here could be just a vector that is made up of a source, right? Or just a sink. You understand? Let's just solve and find out. Okay, so find the divergence of the vector. There's no specified point. The vector itself could just be, the point, the source, or the sink. Let's solve and find out. All right. So first step I'm going to take is to, okay, let me just convert this to the format we are all used to. Okay, so I'm going to express this vector as, now this is the vector f, right? And it's going to be x minus y, that's for the I component, right? Plus x plus z, that's the j component. All right, then plus just z for the k component. Understandable now, right? Okay, so let's proceed. The divergence of this vector, the divergence of f, the divergence of the vector f is giving us the partial differential, or the sum of every partial differential multiplied by the vector itself. That's scalar multiplication going on there, multiplied by the vector itself. All right, so let's see, what does this partial differential looks like? That's going to be the partial differential with respect to x, the partial differential with respect to y, and the partial differential with respect to z, right? Then there's scalar product going on there, and it's going to be multiplying every component of the vector, the ijk component here. Now the first one is going to be x minus y, right? The next one is going to be, okay, I'm going to keep the plus there, x plus, put it in brackets to avoid confusion, x plus z, and then z itself. All right, so this is going to be multiplying this is going to be multiplying this, and this is going to be multiplying this. All right, so let's carry out our scalar product. This is going to be the partial differential of x minus y with respect to x, right? As if this multiply this, and then the partial differential of x plus z with respect to y. Okay, then finally the partial differential of z itself with respect to z. Okay, all right, so let's just carry out the partial differentiation, and we know what this point is like, what this vector field is like, what the divergence at this is like. All right, so what's the differential of x minus y with respect to x? Exactly, it's going to be 1. You know why, right? If you differentiate x with respect to x, it's just going to give you 1. Then you have minus 0 minus, this is a constant. We are not differentiating with respect to y, we're differentiating with respect to x, so every other letter is going to be a constant. Right now, y being a constant, this differential is going to be 0, so we just ignore that guy. Right, so let's differentiate this now with respect to y. Differentiate this with respect to y. All right, so This is x, this is z, there is no y. This is going to be 0, this is going to be 0, 0. Right? Differentiate this with respect to y, you get 0. And finally, we differentiate this with respect to z. Differentiate this with respect to z is going to be 1. The differential of z with respect to z is 1. So we end up having 2. And 2 is a positive number, right? So it's going to be a source, right? We're going to look something like a single, okay, let's say we're working with electric field vector, just a single source, okay, that is diverging away from this point. All right, so that's basically what you do for divergence of a vector, right? You can just take this formula down. It's going to be easier to remember or use. The divergence of a vector, let's say v, right, is the partial differential of, okay, with respect to x, partial differential with respect to y, the partial differential with respect to z of, let's say, the I component, whatever you have attached to the I component, right? Whatever you have attached to the I component, then the J component, whatever you have attached to the J component, you differentiate it partially with respect to Y. Then whatever you have for the K component, whatever you have attached to the K component, you also differentiate that with respect to Z, right? The coefficient of the I component, you differentiate with respect to X. The coefficient of the J component, you differentiate with respect to Y. The coefficient of Z component, you differentiate with respect to Z. Alright, that will be all for divergence of a vector. Okay, see you in the next video where we'll talk about curl of a vector. Bye. Do it to subscribe, of course.